Next we'll come to the heat capacity of a system. Heat capacity. What is heat capacity? Heat capacity of a system is defined as the amount of heat required to raise the temperature of a system through 1 degree centigrade. Of certain mass of substance through 1 degree centigrade, we can say that. Again I repeat, heat capacity of a system is defined as the temperature required to raise the temperature of the heat required, the heat required to raise the temperature of certain mass of a substance through 1 degree centigrade. Means how much heat you require to raise the temperature through 1 degree centigrade. Suppose let us say a substance is there at 25 degrees Celsius at room temperature. You want to increase to 26 degrees Celsius. So how much heat you require to raise this particular temperature? Got it? So that heat is called as the heat capacity of a system. That is called as the heat capacity of a system, which is noted the letter that is C. So C is equal to Q by delta T. Delta T means T2 minus T1. T2 minus T1. This C stands for heat capacity. We can say that. Fine. Now next is, after that we are having the specific heat capacity. Alright, specific capacity. Specific capacity is defined as the amount of heat required to raise the temperature of unit mass of a substance through 1 degree centigrade, or 1 gram of a substance through 1 degree centigrade. That is called specific heat capacity. Alright, unit mass of substance or 1 gram of a substance through 1 degree centigrade, that is called as specific heat capacity. We can say that. Now here, specific heat capacity will denote it with the letter that is CS, so to say. Specific. S stands for specific. We can say that. Specific heat capacity. Now, next is molar heat capacity. From the name itself, we can come to know molar heat capacity. Molar heat capacity means it is the amount of heat required, is defined as the amount of heat required to raise the temperature of 1 mole of a substance through 1 degree centigrade. That is called as molar heat capacity. To raise the temperature of 1 mole of a substance through 1 degree centigrade. That is called as molar heat capacity, which is noted as the letter Cm. M stands for molar. So it is nothing but C by N, we can say that. N stands for number of moles. That is heat capacity by number of moles will give you the molar heat capacity. Alright. Now to differentiate this heat capacity, molar heat capacity, specific capacity, let me take an example and let me explain it to you by help of an example. Let us say I am taking a piece of aluminium weighing 3 gram. Alright. The weight of aluminium is 3 gram and it requires 5.4 joules of heat to raise the temperature from 298 to 300 Kelvin. Alright, I am taking 3 gram, that is weight of aluminium is 3 gram, let us say, clear. So temperature, that is delta T is equal to 298 to 300 I said, na? So that is 2 Kelvin, we can say that. And the amount of heat required is 5.4 joules, Q is equal to 5.4 joules, so we can say that. Now first I am asking you to calculate the heat capacity. Heat capacity is what? That is Q by delta T. So Q is 5.4 but delta T is this. So it is 5.4 by 2. Done. So it is 2.7. We can say that joules per Kelvin. We can say the unit is joules per Kelvin. Done. Now specific heat capacity. So 5.4 by 2 per gram I am asking. So how many gram I have taken here? 3 gram. So into 3. We can say that. That means 5.4, 2.7 by 3. 2.7 by 3, it will be getting it as 0.9. So 0.9 joules per Kelvin per gram. We can say that. Joules per Kelvin per gram. We can say that. Okay. So this is your specific capacity. We can say. Now next is molar heat capacity. It will be 5.4 by 2 into 3. And atomic weight of aluminium is 27. Atomic weight is 27, we can say that. So into 27. So you will be getting to be as 24.3 joules per Kelvin per mole. We can say that. Clear? You can this 0.9 into 27 if you do, you will be getting to be as 24.3 because up to this much is 0.9, 0.9 27 you do, you will be getting 24.3 joules per Kelvin per mole, we can say that. So you can see very clearly I have given an example to you to explain what is specific heat capacity, what is heat capacity and what is molar heat capacity, so to say. Now next is we use specific capacity basically in calorimetry. We use it in calorimetry. So calorimetry is actually a principle by which says that the heat lost in a particular substance is equal to the heat gained by a particular substance. There is an instrument which is known as calorimeter. Calorie is a unit of heat. So calorimeter is an instrument which measures the heat of a particular substance. We can say that. Alright, based upon the principle of calorimetry, what I said you, heat lost is equal to heat gained. For example, suppose this is a hot substance and this is a cold substance. I bring it in contact with one another. I bring it in contact. So this substance is going to lose the heat and this substance is going to gain the heat. So amount of heat lost by this particular substance is equal to nothing but amount of heat gained by this substance. Definitely, it's very simple principle it is. So principle of calorimetry says that amount of heat lost by a particular substance is equal to the amount of heat gained by a particular substance. Now the question is how to find the heat then? How to find? So Q is equal to M into Cs, the specific capacity, into delta T. We can say that. That is T2 minus T1. Alright, T2 minus T1, final minus initial, we'll do it. In this way, where M is the mass of the substance, Cs is the specific capacity of the substance, and delta T is the rise or fall in temperature. Rise or fall in temperature. There is a change in temperature, so to say. So in this way, we use the principle of calorimetry, and there we use a specific heat capacity, so to say. We use a specific capacity in that particular case. Fine. Now, next is we will come to, that is heat capacity at constant pressure and heat capacity at constant volume, that is Cp and Cv. Alright, heat capacity at constant pressure, that is Cp, and heat capacity at constant volume, that is Cv. So the heat supplied to a system to raise its temperature through 1 degree centigrade, keeping the volume of the system constant. Keeping the volume of the system constant, that is amount of heat required to raise the temperature of a system through 1 degree centigrade, keeping the volume of the system constant, is known as heat capacity at constant volume. Similarly, that is a heat supplied to a system to raise its temperature through 1 degree centigrade, keeping the pressure constant, is called as the heat capacity at constant pressure. Alright, so the amount of heat required to raise the temperature through 1 degree centigrade at constant volume is called as Cv, at constant pressure is called as Cp. That is called as heat capacity at constant volume and constant pressure. So when I say Cv, it is du by dt. We can say that's du by dt, because at constant volume we measure the internal energy of the system, and at constant pressure we measure the delta. We can also say delta U by delta T. Alright, here we can say that dH by dt. dH means a small change, we can say that, in enthalpy and small change in temperature. Or we can say delta H by delta T. There is no difference. Alright, so at constant pressure the heat capacity is given by the formula delta H by delta T, and at constant volume this is nothing but du by dt, we can say, or delta U by delta T, because at constant volume we measure the internal energy, already I have said earlier, and at constant pressure we measure the enthalpy, which you have already read it, that is nothing but Qp and Qv, already we have studied. Alright, Qp is your delta H and Qv is your delta U, already we have studied. Now we will see the relationship between Cp and Cv. We'll see the relationship. What is the relationship between Cp and Cv? Okay, fine. Now Cp minus Cv, I'll do it. That is nothing but dH by dt minus du by dt. We can say that. Now we know that H is equal to U plus Pv. From the definition of enthalpy, we can say that H is equal to U plus Pv. And Pv is equal to RT. Pv is equal to RT for when N is equal to 1 for ideal gas law. Now H is equal to U plus RT. We got it? In place of Pv, if I put it as RT, I will be getting it as H is equal to U plus RT. Now I will differentiate it with respect to T. I will differentiate it with respect to T. So when I differentiate it, what will I get? I will get dH by dt. This will be your du by dt. This will be your R, because other one will be RT. Na? The RT means dr by dt, that is nothing but R into dt by dt. So dt by dt is what? 1. So dH by dt is equal to du by dt plus R. Alright, I hope you understood. I am differentiating with respect to T. Now next is dH by dt minus du by dt. We got it as R. What is dH by dt? It is Cp. What is du by dt? Cv. So Cp minus Cv is equal to R. We got the formula. It's a very important formula. Cp minus Cv is equal to R. For 1 mole it is R. For n mole, for n number of mole, it is Nr. We can say that. Here I have taken n is 1. So hence Cp minus Cv is equal to R. For n number of moles, it will be Nr. We can say that. Now, next is if we want to find the atomicity of a gas. We will find the atomicity of a gas. Atomicity of a gas, which is given by the letter gamma. Gamma is equal to Cp by Cv. Gamma is equal to Cp by Cv. We can say that. Now, if the value of gamma is 1.66, mind it is a monoatomic gas. If the value of gamma is 1.4, it is a diatomic gas. If the value of gamma is 1.3, it is a triatomic or polyatomic gas. Again, I repeat, if the value of gamma is 1.66, it is monoatomic gas. If the value of gamma is 1.4, it is a diatomic gas. If the value of gamma is 1.3, we can say that it is a triatomic or polyatomic gases. We can say that. Clear? So, monoatomic is your helium, argon, krypton, xenon, all these inert gases. Diatomic is your nothing but H2O2, N2, Cl2. Alright, this is CO, carbon monoxide, diatomic. Now, triatomic gases or polyatomic gases, nothing but is your polyatomic, so to say. P4, S8, O3 is your triatomic. Even CO2 is triatomic, we can say that. H2S is triatomic, 3 atoms, right? Triatomic and 3 atoms. Now, the question is, how did I get it? 1.66. How did I get? So, we know gamma is equal to Cp by Cv. So, 5 by 2R, the Cp value is 5 by 2R for monoatomic. And it is, the other is your 3 by 2R, the Cvs. Alright, again I write, gamma is equal to Cp by Cv. So, Cp is 5 by 2R for monoatomic gases and Cv is 3 by 2R for monoatomic gases. R cancelled, 2 cancelled. So, 5 by 3 is nothing but 1.66 in this way. Now you may ask me from where I got it. 5 by, there is 2R, from where I got it, 5 by 2R and 3 by 2R, we can say for monoatomic gases. Now 3 by 2R we got it from kinetic energy is equal to 3 by 2 RT. Kinetic energy is equal to 3 by 2 RT, already we have studied in gas laws. Now, so hence when you differentiate with respect to T, what we get? We get 3 by 2 R. Kinetic energy is 3 by 2 RT. Remember it, we have already studied in gas laws. So hence we differentiate it with respect to T. So dt by dt becomes 1. So we get it Cv is equal to 3 by 2 R. Fine, fine. Now next, where we get 5 by 2 R. Now 3 by 2 RT and another that is nothing but 2 into half RT. We will be doing it. That is we will be getting it as 5 by 2 RT. Now why it is half RT, 2 into half RT? Because for diatomic molecule, another what you can say twice is being added. We can say for diatomic molecule, twice of RT is being added. Twice of half RT is being added. We can say that. Clear? So now all these are calculated. These values are calculated. Just for your reference, I am saying you. Otherwise, we find it out by help of experiment. All these values. Got it? So hence we get it 5 by 2 RT. Similarly, for what you can say monoatomic, this one is. Now for diatomic, it will be this will be 7 by 2 R. How did you get 7 by 2 R? Another half 2 into half RT is being added. Alright, clear. So, and this will be your 5 by 2 R. So, R cancel, 2 cancel, 7 by 5 is nothing but 1.4. It is nothing but 1.4, we can say that. Clear, in this way we get it 1.4. That is, this is the value of gamma for which gases? Diatomic gases. Similarly, for triatomic gases will be 9 by 2R divided by 7 by 2R. So, you will be getting 9 by 7. 9 by 7 it comes to be as around 1.3. We can say that. This is around approximation value I am taking it. Alright, so in this way, from the value of gamma, we calculate or we find it out whether the gas is monoatomic, whether it is diatomic or whether it is triatomic or polyatomic. This is the, we calculate the atomicity of a gas, so to say. The atomicity of the gas, we find it out in this particular manner. Alright, I hope you understood how to find the atomicity of the gas. Thank you.